if you're operating a radar at the X band at 9.5 gigahertz, what is the free space path loss for a distance of 11 kilometers? So given the frequency, you can figure out the wavelength. Once you figure out the wavelength, you can figure out the lambda over 4 pi r the whole square. You do the 10 log 10, negative 10 log 10. Essentially, you're doing this equation here. Then get free space path loss of 132.8 dB. You might want to think about it is that this free space path loss, this radar, right, is operating at 9.5 gigahertz. Maybe the object is at 11 kilometers distance. This free space path loss is this guy, isn't it? This is the LFS for this one-word journey. But this object can reflect something back. So there is going to be a RCS here. Some factor of that power is going to be reflected back. And then the journey is another LFS. There's a loss of 2 times LFS. That means this term will become to the power 4. You'll get lambda over 4 pi r the whole power 4, something like that. You'll get a power factor of 4, because there is 1 over r square in the forward leg, and there's a 1 over r square in the return leg. So radar, since the loss is 1 over r power 4, this is a very bad news, because if you want to extend the range of the radar, let's say even if you want to extend the range of the radar by a factor of 2, that means the distance where you can detect a target, that distance range, if you want to extend it by a factor of 2, then your power, the transmit power, has to go up by a factor of, it has to go up by a factor of 2 to the power 4, which is 16, yeah? You need to have 16 times more transmit power just to be able to increase the radar range by 2, yeah? So that's why all these military radars, those are very high power RF devices. They're very expensive.